I'm being serious. She was like, man, I wish I had a chalkboard. I was like,
All right. Oh, it's just lagging. Okay, so the internet's just being slow. Okay, so there might be a bit of a lag between what I write and what it actually shows up. Yep. Okay. So what we're going to do is that we're going to take this formula that we just made up and we're going to graph in Desmos. So you're going to type in the formula exactly as you see it, just without the V equals. So I'm going to have Desmos pulled up. And I'm going to type in x times 24 minus 2x times 18 minus 2x. All right, and then I'm going to expand my window so I can see all of my maximums and minimums. You may have to like zoom out, zoom in, fit the window. We're going to have to move the window around a little bit. So let's say that the x's go up to about... So we got to go from 0 because we can't have a negative. So we're going to go from 0 to... what was the highest height we could say we had? So what was the biggest box we said we could have? An 8 by 8. So I'm going to put my maximum X as 9 or 10 so that we can see the window clearly. All right. Then your Y's, I would just go up to about maybe 1,000. So I would say go from about, let's say -1 to 1,000. Or, yeah. All right. So I just set my window to be basically what we already said the dimensions were. The reason I put the y-axis to about 1,000 is just so I could see it better. All right. Now, we want the relative maximum. So Desmos should already graph it for you. And if we do that, we get this point. All right. If we round to the nearest tenth, so 1 decimal place, what would my point be? So if I round these two numbers to the nearest tenth, what would the point be? So 3.4 and I would just say 655 because it kind of rounds down. So what's the maximum volume that can be made on this size of paper? So our max in this case from this window, we looked at it from a window of 0 is x is greater than 9. And then 0 is less than y, which is less than 1,000. This was the window that we looked in. And why do we look at that window? So my x values represent my height. First off, can I have a negative height? No. When you're dealing with measurement, you can't have a negative number. And then what was the biggest box I could make? 8 by 8. So I did one more just so I can kind of see it a bit better. Now, and again, 1,000, I just did it because just so we could see it. Sometimes you just want to do a fairly big number so you can see it nicely. All right, so that's the window that we put. And our max point was 3.4 by 655. So here's my question. What is the maximum volume that can be made with that size piece of paper? It comes from that point. Which part of that point do you think that is? The x or the y? It would be the y value. Because we already said x is equal to what? So up here, up at the top, x is equal to what? Your what? X is equal to our height. So x is equal to your height. All right. Thus, the biggest volume we can make is 655 squares cubed. And the maximum volume, the size square is a 3.4 by 3.4 box. That's the biggest box that we can make. That would give us the maximum volume. That's the big, Lord, too many geometric words. That's the biggest square we can make to have the maximum volume. Yes.
What is that? Let's say 1, 2.
What?
Like, what is it? It's too small sizing.
Now, let's talk about the x-intercepts of this graph. So if I zoom back out to fit my graph and then zoom out a little more so I see all my x-intercepts. I have 3 x-intercepts. All right, I have 0, 0, 9, 0, and 12, 0. So 0, 0, 9, 0, and 12, 0. What do you think those meanings are? So in terms of the situation, what do you think this meaning is? Well, think about it. Your x values represent your what? What I just say the x values in the situation represent? It represents the height. X represents the height. All right, that's what it will always represent this situation. So if I have a height of 0, that means what? I have not cut the paper, right? So if I have a height of 0, that means I have not cut the paper. All right, what does the 9, 0 mean in this situation? So we said the biggest width that we could cut out was 8 by 8. Why could we not cut out a 9 by 9? Because it'll do what? It would be 2-dimensional. So 9 by 9 means we no longer have a width. Now, it is possible to do an 11 by 11 or a 10 by 10 box. All right. Because it still would make a box, just a albeit very, very small box. So if I did a 10 by, what would a 12 by 12 do? So think about it. What was the length originally of the rectangle? It was 24, right? Come on, guys. Wake up. Come on. We're almost done. So it was 24, right? And 12 is what to 24? So what do you think happens if I cut a 12 by 12 box? We no longer have a length. All right. So, in other words, their meanings are the max width and the max length possible for x. All right. Now, we already said what x represented. What does x represent? X equals height. So if I'm talking domain in this situation, what is the smallest height I could have? Could I have 0? I mean, I could. Just means I haven't cut the box yet. So we're going to say it goes from 0, but put a parenthesis on it. Because remember, if you put a parenthesis on it, it means it gets really, really close to 0, but we just haven't hit 0 quite yet. It's not going to hit 0. Because we can still cut off, say, like 0.5 of a box. 0.5 by 0.5 of a square. What's the highest number it has to be? Or what number can it not go past?
I was kidding. 12.
It can't go past what? 9, right? So we could technically have, guys, listen, we could technically have cut off slightly bigger than an 8 by 8 box. We could have done an 8.5 by 8.5. We just can't do 9. So if we're looking at our graph here, all right, we don't really care about what's between 9 and 12 because that's in the negative. We don't really care when it's greater than 12 because it doesn't apply to the situation. What we care about is what's happening between 0 and 9. That's our domain. All right. Now, what do you think the y represents here? Y represents our what? What were we finding this entire time? The what? Not the area. The volume. So, what could my possible lowest volume be? What's the only thing a measurement cannot be? Negative. So our lowest could possibly be about 0, but we're going to say it's not quite hitting 0, so we're going to use a parenthesis. But what has to be the highest? Where is it cap? So what's my highest y value? Where is it cap? What do we say up here? What's my highest y value? What do we say up here? 655. That's my highest y value. And we're going to put a bracket on this because it caps there. It does not go past 655. That's the max volume you can get. You can get anywhere between 0 and 655 depending on your dimensions, but you cannot go past 655. Does anyone kind of get how I got the domain and range appropriate for the situation? All right. So if we generalize this formula, that means we would have x. I kind of already wrote up top. Then you take the length, subtract 2x, take whatever the width is, subtract 2x, and that would give us the volume. That's what we can use every time to find the maximized volume. All right. Okay, we're going to take a 5-minute break so you guys can wake up a little bit. And then we're going to come back and do one example together, and then I'll throw you into Delta Math. All right. So be back before the timer goes off.
Look at the box. And you can like visualize. Oh my god, I love that. How much you need this? I'm forgetting everything. Come on. Sorry. Come on, I'd like you.
Because I need to go to Guatemala to
What are you going there for?
because I have family down there that I cannot communicate with or interact with.
I'm just curious, I'm sorry. You
So
don't have to answer. I'm just asking.
I guess for no reason, I guess. I go there and I sit and I learn.
But to hang out with your family.
So, Tomas, most of the rest of the notes will be in your packet. And then just, I don't think I'm going to be getting any other. No, you're not getting any other handouts, so just check Canvas whenever you get a chance.
Miss Murphy, I made you a visual box. Really cute. Don't you shake your hand at me, gang. I'm trying to have Miss Murphy, everyone in unit. How many of these fits into this? Let's find out.
A lot.
What?
More than we have enough for.
What? What? We can make them. Do you want to make little cubes with me? Madeline, do you have a thing with the pad of graph paper? A pad of graph paper. I don't, but I wish I did.
Oh, I have one. So, not with me, but I have one somewhere.
Can we just make a bunch of little cubes? Gang, oh, there's tape on the shirt. Oh, there's aliens. So little squishy.
Yeah, there's air in it. Like, how I didn't put it in a vacuum chamber. Like, it's like that.
Feel it.
It's like a tape. It's like a banana tape.
You know what I'm talking about. I want to make more cubes.
It's like, and I cut out index. I cut out index cards. This clothes. So I'm just going to use the cards now.
Okay, my question is, why did you cut them so? Why did you cut them? Oh, wait. Never mind.
It's excited.
It's a cube. You're a cube. What do you mean?
What?
What are they doing? I didn't do anything.
Wait, is it?
It reminds me of that was in, was in Fez. Fez? Yeah, it's a little game. You go around and you can like create like cameras. It's like a little parkour that you have to cheat. Get your hands on.
Cancel for what, gang? Why are you bored of me?
Yes.
Me.
Miss Murphy, do you like the unit box?
Huh? You didn't make that.
Yeah.
And I made her a visual cube. And then
You know what
she-
we can do? We can
I
stick
made-
him in the little bowl
I
and
made
read
this.
Miss Murphy.
I made this. I was like, oh my god, it's visual, and you can see it now. And she sighed.
It works, I don't care.
What?
I was doing this to keep What? Miss Murphy, we can make a bunch of these and stick them in a little thing I made. No? She said, you don't want a bunch of little cubes?
Wait, I want them.
We can make
You make these songs?
Yeah.
Alright guys, let's get back to, we're just gonna do one example problem together just to kind of put that formula that we just came up with
Into action. So that entire activity that we spent going through the first part of class going through gave us this formula. This is like the whole point that we get from that entire activity. All we want to know is that if the height is equal to x, which is the size of the box that we cut out, an x by x box, we would take the original length and then subtract the 2x from it, so 2 times the height, take the original width and subtract 2 times the height to get the correct volume that we need. And that would be the function that we would graph to find the maximum volume. All right. So let's do number 1. So paper size. We want to write a polynomial. So we have an 8 by 8 by 11, not 8 by 8, 8.5 by 11 paper size, which that's a pretty standard piece of paper. So if you had a piece of paper in front of you, that's typically the size of a piece of paper. All right. We want to find the maximum volume we can make if we took out some squares on that piece of paper and made a box. So what would be the formula that I would have? Volume would equal what? So what would the height be? What's always the height? So remember, when it comes to volume, we have height times the length times the width. I know it's length times width times height. Right. So we put x first. Now, what do we use to represent the new length? We do what? How do I find the new length if I take out an x by x box? What does this formula up here say for me to do? So, how do I write out the new length? What does this formula tell me to do? Right. Right. Take your original length, which in this case is 11, subtract 2x. So how do I get my new width? Same thing, but with the width. Take the original width, subtract 2x. That's all you got to do. So up here with this formula, x is your height. This L is your original length. And this W is your original width. All right. These as a whole is your new length. So I'll say new L. And this as a whole is your new width. All right. So they're going to give you a length and a width. And they're going to tell you, we're going to cut out an x by x box. So how do I find the maximum volume? And that's when we're going to put it in Desmos. So we're then going to graph this in Desmos. All right. So we're going to graph this in Desmos. So graph in Desmos and draw a quick sketch of the graph. So in Desmos, I have, we essentially already have it set up. We just got to switch out the numbers. So in Desmos, I have 11 minus 2x times 8.5 minus 2x times x. All right. So if you already had the first one typed in, all you got to do is switch the numbers out. Now, I'm going to graph my x-intercepts first. So I have 0, 0, 4.25, and 5.5. So I have 0, 0. Let's say this one is 4.25, and this one is 5.5. And then my graph looks something like this. All right, good. Now, where's the only part of the graph that I care about? If I want to find the maximum volume. What's the only part of the graph that I use to find the maximum volume? What's the only part of the graph I care about? We only care about this part right here. Why do I only care about that particular peak right there? Because it contains the what? The maximum. We only want the peak that contains the maximum. What is that maximum? What does Desmos tell us? So guys, you should have already graphed this in your graphing calculator. But for time's sake, I'm going to give it to you. So in Desmos, I'm looking for the maximum, which is right here. So let's round to the nearest 10th. So 1 decimal place. What's the point?
1.6.
By? Right. So my point here is 1.6 and then 66.1. So letter C says record the X value that you should cut to maximize the volume. So what is my X value? X has to equal what? What's the X value of my max? 1.6 inches. What would be my maximum volume? V would equal what? 66.1 inches cubed. Now, given the domain and range, what do you think my domain would be in context? We're only using the part that I care about. So my domain would be what? From what two X values? Look what I circled in blue. Right, it'll be from 0 to 4.25. And we're going to keep those in parentheses because they can't quite hit either of those numbers. Then my range would have to be what? So look from where I circled. What's the only viable range? So we're still looking at what I circled in blue. You're close. So 6.61 is the highest, but what's the lowest Y value we can possibly have? 0. So this will be from 0 to 6.1, and we're going to put a bracket on that because it caps. So guys, every time you do a problem like this, all you do is take the original width and the original length and put it back into this formula. So X is always your height. You take your length, subtract 2X to it. You take your width, subtract 2X from it. Put this equation into Desmos. Find where the maximum is. The X value gives you your maximum height that you can have to make the maximum volume. Your Y value is your maximum volume you can make. All right. And then your domain range goes from 0 to whatever your first x-intercept is, or wherever that maximum is in there, which is usually your first x-intercept. And your range is always from 0 to whatever your max height is in context. Does that make sense? That's pretty much all I got to do for problems like these. Any questions? All right. So for the rest of class, you got like a solid 20 minutes. There is a quizzes on this. It's already posted. Should be labeled 7.1 open boxes. It's pretty much the exact same process that we've been doing. You're just using that formula exclusively and Desmos. So you may want that open. And I'll go ahead and post your exit ticket. So for problems like these, Desmos send you to your friend. For the boxes that you made earlier, you can chuck them. Just make sure all your trash finds its way to my trash can. Yep. I mean,
One of my little boxes. This box is cute. It's very so cute.
okay.
Fix him. I'm really broken.